Okay, and we're live. All right, so we got uh, Andrew Higgins, Jeff Greason, Lucas Beveridge, and myself here to talk about that hecka. Talk about advanced space propulsion and nuclear power, and some of the stuff that's happening at NASA right now, and Jared Isaacman's priorities and hopes around nuclear electric propulsion. And I'm just going to ask everybody to just briefly introduce yourselves. Andrew, if you want to go ahead and start that off.
Sure, I'm Andrew Higgins. I'm a professor of mechanical and aerospace engineering at McGill University up in Montreal, and I have an interest in do some research in advanced space propulsion.
Jeff?
Yeah, I'm Jeff Greason. I've worn many hats over the years. I've done computer chips. I ran a reusable rocket company for a while. I've done space policy stuff. I was on the Augustine Commission, and I have been working in advanced space propulsion for the last 10 years.
Lucas?
I'm Lucas Beveridge. I'm a nuclear engineer. I currently work at X Energy. I've done a lot of space nuclear work in the past. In fact, that's the reason I became a nuclear engineer. Prior to that, I studied space propulsion and advanced propulsion, things like that.
Awesome. Well, thank you all for joining me here. And this was, I just want to mention, this was Andrew's idea, Andrew, so I'm going to throw the ball to you and ask you to take it away.
Sure, thanks, Ozan, and thanks for setting this up. This would be beyond my technical abilities to do something like this. So what brought this meeting about was a big announcement last week on Tuesday. So the new NASA administrator did a major refocusing of the U.S. space program. I think overall it was pretty well received by the community. I think the postponement, or in other words, cancellation of the Lunar Gateway, was kind of the other shoe we were all waiting to drop. And accompanying that was an announcement that the new administrator, Jared Isaacman, has been preluding for some time, which is doing a demonstration flight of nuclear electric propulsion. In other words, flying a nuclear reactor in space to then power electric propulsion like an ion drive or a Hall effect thruster. And this would reuse some of the hardware that was developed for the Gateway. The Gateway would have used a Hall effect thruster in a space demonstration of this concept, which we'll call NEP for short. I like to avoid acronyms, but we'll be using this a lot probably. So this is where I had some skepticism. First of all, the timeline was to fly this by 2028, which is an aggressive timeline. This is an aggressive new administrator, so I'll be willing to give a pass there. My greater concern was that it was billed as advanced propulsion research and that it would be used for a mission to Mars to deliver more helicopters to Mars. So I'm all in favor of putting more quadrotors on Mars and doing more science, but it's really not possible for any nuclear reactor that we would fly in the coming years to contribute propulsively to a mission like that. So just to put all my cards face up, I'm very pro-nuclear. Okay, back in 2018, 2022, I was in San Luis Obispo fighting to save Diablo Canyon. Okay, so I am as pro-nuclear as you can be. And I'm also a believer that we will need nuclear power in space. So in permanently shadowed regions of the moon, or you're going to go to Mars and do in situ propellant production, or you're going to go to the outer solar system, having a nuclear reactor in space would be very desirable. But when it comes to applying nuclear power to propulsion, what really matters here, the key metric is the specific power, how much power you get from the mass of your reactor. So we'll use these numbers a lot, usually expressed as kilowatts per kilogram. Just to warn you, if you dive into the aerospace literature, a lot of times it's reported as the reciprocal of that, the alpha parameter, which is kilograms per kilowatt. But I'll try to keep it in terms of power per mass, because that makes a little more sense. And when you start trying to do mission optimizations for rapid transits in the solar system, so you really want to try to get to Mars faster, the key metric comes out to be you need something like a kilowatt per kilogram. So each kilogram of your reactor has to produce on average a kilowatt of power. And that's a pretty tall bar to cross. So most of the designs we have for nuclear reactors that would operate in space come out around 10 watts or 15 watts or 20 watts per kilogram, meaning they're about a factor of 100 short of what you would need to do a propulsive, meaningful propulsive maneuver to get to Mars. And the issue here is just that to get a lot of thrust out of an ion engine, you need, or a Hall effect thruster, you need a lot of power. And if your mass of your reactor scales with that power, then your reactor gets heavy. And because of that, you're limited in the acceleration you can achieve. So if your mission is going to last many, many years, that small acceleration can accrue to a meaningful delta V. But for a Mars transit that would maybe last 6 months or 8 months, it's very difficult for a nuclear reactor to contribute to that. So I think it's just a bit of a misapplication of nuclear electric propulsion. So again, I'd almost give a pass because nuclear reactors in space, useful technology. My concern is that is being sold as the propulsion element. Okay, and there is a need for advanced propulsion. We need to get fast chemical rockets to do missions deeper in space, and there really hasn't been much technology demonstration flights done by NASA. So NASA, for example, has wanted to fly a solar sail since the 1970s, and it's never been done. There's been a few ride shares, but there's never been a dedicated solar sail mission. And there's probably about a half a dozen other technologies that would be really, really nice to see fly to advance propulsion concepts. And just my concern is I am concerned that this could become another albatross that ends up sucking all the oxygen and all of the funding out of the room if everything that is, everything we think about advanced propulsion says, oh, well, that's our nuclear electric propulsion program. So that's my concern. At the same time, while it's difficult for nuclear reactors in space to hit this magic kilowatt per kilogram metric, solar panels are almost there. So there's a company called, what are they called? Starlight or Starflight or something that just last month announced they are selling thin film solar photovoltaics, so solar panels that generate up to 3 kilowatts per kilogram in Earth orbit, right? So as you move further away from the sun, yes, sunlight goes down as the inverse square distance, but for use in the inner solar system, they're already kind of at that metric. Now, again, this is just the thin, flexible film. How do you support that and so on is going to add mass on. But it's an area that's evolving quite rapidly, and I think it will continue to evolve because, as we know, there's tens of billions of dollars of R&D going into solar photovoltaics. So I see that as like, really exciting emergent area, and you can use those solar panels to drive your ion engine or Hall effect thruster just like a nuclear reactor can. To the first order, electric propulsion is sort of agnostic to where the electrons come from. So that's kind of the backdrop. That's my concern, is that if we put, if nuclear electric propulsion becomes the flagship for NASA's advanced propulsion research, going to suck up all the funding. I can't see anything else flying when this is this is the only game in town, and worried it's going to have implications that could last decades. So I went online and started ranting about this when the announcement was made last Tuesday. I got some pushback from Lucas, who knows much more about nuclear reactors in space than I do. So rather than getting to a hissy fit on social media, I thought it best be better to pull people who know more about this than I do into an online room like this, and let's get into it and hash it out. So I think maybe I'll turn it over to Lucas at this point, and maybe my first question to you, Lucas, before we get too much into the technical details, do you think it's feasible to do a technology demonstration flight like this by 2028 in the next 2 years?
Yeah, I mean, they have everything going for them. One of the nuggets I got last week was that they are using an existing reactor design, so there's no new development at all. So they're using an existing design that has existing supply chains. So they could theoretically start ordering hardware right now, right? The DOE has their own fuel supply, so that's not an issue. Heat pipes and Greason, that's all relatively mature stuff. If they needed it to operate for 10 years in space, it probably wouldn't work. But their design life is 1 year, so that's very doable. 20 kilowatts is also very low power for any reactor. Like even research reactors are way higher than that. So yeah, 20 kilowatts is very, very doable. They have everything that they could. They could hypothetically do this. Obviously, they have a spacecraft bus from Gateway, so I think they could. My only concern would be INL. They have not such a great track record recently of delivering stuff, so that's my only kind of concern.
Could you fill us in on what INL is, maybe a little bit?
It's Idaho National Lab, and they're the ones who build the RTGs as well. They're the primary integrator. They take the plutonium and build the RTGs that they use on the Mars rovers and so on. And they have a lot of talent that does space nuclear related stuff.
Should we take a moment to tell the audience what RTGs are?
So the radioisotope thermoelectric generators, they use radioactive decay, usually from plutonium-238, to generate electricity. They're very low power, but they work anywhere, and it's basically a battery that you plug in. It doesn't require any active control. It just generates power. So because of that, INL has a lot of space nuclear expertise and people there. So it kind of makes sense that they would be the ones doing this. I think, at least I'm assuming they're the ones that are going to be doing this. NASA just said it's NASA DOE project. But, that would be my only concern. They've had other non-space nuclear related projects that are way behind schedule recently, like the Marvel reactor and stuff like that. That it gives me a little bit of concern that they might not be able to do it in time. But then again, this is such a simple thing; they should be able to do it. And part of the reason is that the DOE can indemnify the launch and everything too. So if they went to a private company to develop the reactor, there's no existing legal structure for indemnifying the launch, which is part of the reason. So they had good reason for sole sourcing it to the DOE, but that would be my only major concern. Long story short, yes, I think it's feasible. They should be able to do it.
Okay, maybe another question I would ask for you, Lucas, is as you all know, there's not a great history about doing nuclear electric propulsion demonstrations. And to his credit, Jared Isaacman referenced this in his announcement last week that NASA has not the greatest history on this. And I believe what he was alluding to was something called the Prometheus project. So there was a NASA administrator a few administrators ago, I think it was Sean O'Keefe, who also was a believer in nuclear electric propulsion, and started to push the concept of doing a mission called JIMO, the Jupiter Icy Moon Orbiter. So this would have been a very ambitious mission that would have had I think 200 kilowatt electric reactor. This was the Project Prometheus part of it. And it would have gone to Jupiter, and then it would have individually orbited the different moons of Jupiter. So that's the kind of mission for which nuclear electric propulsion almost makes sense. You would go in orbit around one moon and then leave and go into an orbit around another one, similar to how solar electric propulsion was used by the Dawn mission to go visit one asteroid, Vesta, and then go visit another asteroid, Ceres. So when you have missions that last many, many years, the benefits of using electric propulsion coupled with either solar power in the inner solar system or nuclear power in the outer solar system starts to make sense. But what happened there was about $700 million was spent on that Prometheus project, which produced essentially PowerPoint slides, no hardware. And the budget they came back with to do the entire mission was over $20 billion. And at the end, the planetary science community said, we don't want to have anything to do with this. We would like to go to the moons of Jupiter, but we would much rather do individual missions using conventional chemical propulsion that would come up being cheaper. So that's where I think a lot of the skepticism that was surfacing in the media last week came from. And I'll give a shout out here. The author, David Brown, who wrote the article last week in Scientific American, I was quoted in, wrote a great book called The Mission about the development of the Europa Clipper mission. But he has a good chapter covering the sort of the debacle around the previous JIMO mission and the Prometheus project. So how do we avoid a repeat of that, Prometheus 2.0?
Do everything in the opposite way, basically. There was actually a really great report that was published by INL last summer. It was written by Bobby Lal and Roger Myers. It dives into the history of that and analyzes basically what has gone wrong, not just with Prometheus, but like every space reactor program in the last 50 years. They've, SP100 and Timberwind and all these others. What typically happens is they try to overreach. They get too ambitious with their initial requirements, like let's go to a megawatt or 200 kilowatts or whatever, and it's got to last for 10 years and everything else. And that was kind of an issue with the FSP program that NASA did a few years ago. It's like, well, it's got to survive on the moon and generate. I mean, the power requirement was only 40 kilowatts, which is fine, but they wanted it to last for, I think it was 10 years, and it had to have all these other requirements. It had to be like shielding because there's going to be people nearby and all this. So that's typically what happens. They overreach, and it ends up spiraling out. And you have to take smaller steps, basically. That was the gist of that report. I can tweet out the links to that because they're.
Yeah, if you can put the link, maybe Ozan can collect all the links and we'll put them in the description in real time or certainly after the session's over. So Lucas, we will want to drill down here in a minute on. We're going to get into kilowatts per kilogram and radiators and all these issues. But before we get too technical,
so Andrew, I just wanted to mention that we do have live chat.
Okay.
So if you guys pull up YouTube on the side muted, you can see some of the comments and questions that are coming up. I'll try to speak out the technical questions that come up. I won't echo all the comments, but there's a question about nuclear thermal propulsion. I don't know if you guys want to kind of tackle that now or when we go.
I mean, I can try to take it really quick. I think it may be good to differentiate this for the audience. So there's two traditional ways that nuclear power can be used for propulsion. So one is nuclear thermal propulsion. Basically, you're using your nuclear reactor like a steam kettle to heat a propellant that you expand through a nozzle. So that, if you've ever heard of the NERVA program from the 1960s or ROVR, there you can generate quite significant thrust. There the thrust is measured in kilonewtons, thousands of newtons. The thrust to weight ratio of the rocket can approach or even exceed 1. So it's like a dragster. Okay, you can really turn on the torque or the thrust when you want it. And there was, over the last couple of years, a program called Draco, recently canceled, to try to resurrect this concept. One of the bugaboos there is, how do you test the reactor? So in the 1960s, they just went out in Nevada and tested the reactor with exhaust, and it would be difficult to do that today. And so you would probably need a dedicated test facility, very likely in the Idaho National Lab, where Lucas mentioned, and doing that kind of testing, again, pushes us up into the billions of dollars. The other issue I would say about nuclear thermal rockets is, well, their specific impulse is impressive, can be, I think NERVA was around 800 seconds. I think now with modern materials, carbide, ceramic carbides, we can operate at a bit higher temperature. We could push the ISP up to 900 seconds. While that's impressive, it's twice what chemical propulsion can do. We're also now very close to the era of rapid reuse of launch vehicles. And so just delivering more payload to orbit, which is, we're going to pull Ozan into this in a minute here, may just be more feasible than using a higher efficiency upper stage like a nuclear thermal rocket. So what we're going to talk about today is nuclear electric propulsion. Here, the advantage is the reactor can be tested on the ground safely. It's really no different than running a conventional nuclear reactor that we use to generate electricity, just a smaller scale. And then when it's up in orbit, you can just mate it to an ion drive or a Hall effect thruster, and it should work. Maybe there's a surprise waiting there, but it should be plug and play, or at least as an outsider to me, it would look that way. So it's, in a sense, more technically feasible, but usually when you do comparisons to the missions, at least in the inner solar system, nuclear thermal wins out. So if you want to deliver more payload to Mars, probably nuclear thermal would beat out over nuclear electric. So we'll probably get more into the technical details here. Before we get too technical, I want to pull Jeff Greason into this because Jeff is probably more than anybody I know has been highlighting for a long time, decades, that NASA at its creation, something was skipped, which was a role that was previously filled by its predecessor organization called the NACA, which was to do technology development and demonstration of new technologies that were too far of a reach to be done in private industry. And
it's in the NASA charter. Improve the performance, utility, speed, range, et cetera, of aerospace vehicles. It hasn't been a big focus.
So is this what you want, Jeff? This SR1 Freedom? Is this your vision of what a technology demonstrator mission for NASA would be?
I'd like to save answering that question for the end. I got a few more things to say about it first. I have to put that in context. Engineers tend to look at engineering decisions as if the engineering criteria were the only thing you had to take into account in making the decision, right? But NASA is an organization with a lot of constraints, and they aren't all technical in nature. It's not like this big pot of money that the administrator just gets to decide how to spend. That money is earmarked. The money is not fungible. He has to balance how much of the budget goes to various centers. He has very little flexibility in that because if he changes too much, Congress gets unhappy. So there's a big difference between asking the question of, if you had started from a blank sheet of paper, what would you do? And saying, starting from where we are, what would you do? The things that you said about about particular near-term nuclear electric, with a quick diversion here, that the parameter that drives all this is really the temperature that the reactor runs at. If the reactor runs at a low temperature, it's easy to do, very small step from the things that we're doing now. But if you try to run it at high power levels, you need a lot of radiator area to make that cycle run. That's what makes it heavy. That's what makes the specific power low. Are there things we could do to bring the temperature up and bring the specific power up a long way? Absolutely there are. Are there the things they're going to do first? Absolutely they're not. Should they be the things they do first? Absolutely not, for the reasons that Lucas pointed out. If you make this too ambitious, it'll turn into another big giant project that everybody and their brother wants to be a part of because they know it'll last forever and they know they can't be blamed for when it fails because everybody will be retired by then. So because of this enormous record of failure after failure after failure, programmatic failure, where every attempt to do nuclear anything that NASA has done has come to tears. I think the psychological effect of just fly something, if successful, would be very significant. And if you want to fly something, the only way to do it is make it fast, because if you make it a 5-year project, it'll never happen, because then the next thing you know, it'll be a 10-year project, and then you'll have a change of administration, and it'll just get canceled again. So speed is life. You either fly fast or you don't fly. And the only way you can fly fast is to slap together pieces that are more or less what you already got in the pipeline, like Chris was saying. Grab the electric propulsion from here and the heat pipes from there and the reactor core from here, put it together and go. Will this demonstration of that technology perform an interesting mission? No. Did the X-1 carry passengers or bombs? No. The purpose of a technology demonstration is to demonstrate technology. If you get a mission out of it, that's gravy. We're not going to send the first one to the outer solar system because you'd have to be, not just, it wouldn't just have to last 10 years. You'd have to prove that it lasted 10 years. You'd have to prove in a year that it was going to last 10 years. You can't do that. So again, the only thing you can do is send it to a nearby destination. So it's going to be Mars. And if we have some payloads that we want to take to Mars to give a ride, that's wonderful. That's gravy. So I think this is programmatically a pretty good bet, because I think it would have an important effect even though the technology demonstrated for this mission is not necessarily optimum for purpose. Another thing I want to say before I yield the mic is, one of the big things going up the works in U.S. national space policy for decades has been, we don't need any more big government rockets. The private sector has the rocket game under control now. We have a big NASA center whose purpose in life is making big rockets. We have to find something for them to do.
This is Marshall for.
This is Marshall. We have to find something for them to do, and it has to be an expensive something. Because there's no way that their budget is going away. So either we give them something expensive to do, or we keep building government rockets that we don't need. There's a lot of advanced technologies I'd love to see NASA working on, as we all know. But mostly they're cheap to work on. That's why they're so exciting. Nuclear is the expensive one. So you have to start a nuclear program. Why don't we do it for nuclear surface power? Because if it was nuclear surface power, it wouldn't go to Marshall. The only way to make it go to Marshall is for it to be propulsion. So we have to have a nuclear propulsion program. The fact that you can then use that same reactor to do surface power, well, isn't that nice? So again, I think this is a rather masterful playing of the pieces that are on the board, playing the hand that he's been dealt, to achieve a useful result.
Okay, I got to say this gives me a bit of deja vu of how we got to SLS and Artemis. Playing Kerbal Space Program with the existing contractors and hardware that we have is where we got us to where we are today, which today is a pretty good day, right? We're coming back from the moon.
It's not a perfect world. It's not a perfect system. It's not a perfect appropriations process. You can either get upset about the 90% of money that gets wasted, or you can get excited that maybe we're going to move the fraction that's useful from 1% to 10%. I choose to put myself in the second camp.
Jeff, I was going to ask you a question, but I think your last statement kind of made it mute. The question I was going to ask is, you brought up X1, which is the first Mach 1 airplane that was product of the. It was basically a rocket plane that was the Chuck Yeager plane that broke the sound barrier. And now what I recall from reading about that was that there was a learning experience there about how do you design an airframe to efficiently move at those speeds, as well as making it pilotable, and actually testing it at those speeds. There were lessons learned, right?
Absolutely. There's a little bit of legend about that. Chuck Yeager likes to make it all sound like it was something done in the field. Most of that invention was done by the unsung, heroes, the aerodynamicists and the designers behind.
Okay.
First off, the and projects of the NACA, they talk about agency that NASA. Thought are correct. The rocket airplanes were trying that we were going to use to do this. Keep seeing us ban it here. Okay, so was that the right technology? Was that the perfect?
The connection was problematic, as I wasn't hearing you very well, but I think
I had that problem too. But you all seem to be back now.
Okay.
So
we had a comment in the live chat that said Jeff has turned into a robot. So I think
you might need to back up. You might need to back up and restart there.
I will back up a little bit. So the X was a joint Army Air Corps NACA project. So it was one of those projects of the predecessor agency, and it's kind of an example of a good parallel.
I think did we lose Jeff?
Yeah, I think we're losing Jeff again.
Okay.
I don't know.
might need to have Jeff access from a different route. Ozan, well, we're working out Jeff's connection. Let me pull you into this. So Ozan, you're always my go-to guy when I need to have my enthusiasm about some new advanced space propulsion concept. Rain on my parade, right? So every time I get excited about a mission or a new a way we might do space propulsion, Ozan always comes back and says, well, really, in the era of Starship, we don't need your new advanced propulsion idea. So really, I've sort of under Ozan's influence come to the conclusion that if we're in an era of rapid reusability of orbital capability, and we can do on-orbit propellant transfer, and you can do in situ propellant production on Mars, we can really do almost anything you want to do in the solar system. I mean, even sending a crewed mission to Titan, the moon of Saturn, is really not out of the question in the Starship era. And if for whatever reason the Starship program should falter, there's other companies, as we all know, waiting in the wings, ready to pick up the torch and advance it forward. So, Ozan, is there really anything that would get you excited about nuclear electric propulsion that would enable us to do things we can't otherwise do?
I mean, I would really like to see something like an Oort cloud mission, catch something really fast coming through the solar system, because you can do a flyby with chemical propulsion. You can actually do a fairly efficient flyby of a fast-moving object, even catching up to something that's pretty far out with chemical propulsion, and a powered Jupiter gravity assist. So you just kind of swing around Jupiter, and you essentially draw a little bit of Jupiter's energy shooting out of the solar system. You can get really, really fast. But then slowing down once you're out there is a problem. And you're far from the sun, so any kind of solar electric or solar thermal propulsion is really difficult. Even laser thermal propulsion, which I'm excited about, wherever your power source is, it's going to be pretty far. So just concentrating is going to be difficult. That seems like a really good application for nuclear electric. And even in general, outer planets missions, it's at this point, in terms of near future technology, it feels like nuclear, electric, and chemical is a little bit of a wash. But I could certainly see that balance shifting in favor of nuclear as the power densities improve.
Okay. Yeah, I see Jeff sent us a message there. He's waiting to get back in, so maybe you can readmit him.
Thank you for your point.
Okay.
I've been listening the whole time.
Okay. Yeah, Jeff, we want to try to capture your earlier comments there about the backstory of the X1 and the role it played. I think.
Are you reading me now?
That?
Yes.
Yeah, you're coming through loud and clear. Yeah.
Okay. So, the X1 was a joint NACA Army Air Corps project. So it was done by the predecessor organization of NASA as an example of flying something to gain the necessary flight experience. And it's kind of an interesting parallel because nobody thought then correctly that rockets were the way operational aircraft were going to be flying around in supersonic regime. But it was what we had to do to get into there to prove that it could be done. They put together the pieces they had to go out and show that it could be done. And once it was done, within a very short time, we had operational aircraft operating in that flight regime. So I think there's merit. And I'd love to see NASA doing a lot more of this. I mean, I think Andrew's concern that this will suck up all the money in the room is a legitimate thing to be worried about. But you have to recognize that when it comes to demonstrating useful technologies, there's currently no money in the room to suck up. NASA's not doing this work. So it's not a question of if they do this work, they'll stop doing all the other wonderful things. There aren't other wonderful things. Would I love to see a broader push, a bigger portfolio of technologies invested in? Absolutely, I would. And I think that that would be a wise use of NASA funds, because most of the other ones are much cheaper than this. I think this one's being announced first for the reasons I talked about, that you have to find a large project to do at Marshall, and it might as well be a useful one. And I think that's why this is the first thing. Bear in mind that it's still quite early, and in time as NASA administrator, there haven't been a lot of new appointments made, and he's, to put it mildly, had a very full plate since he got in. So there's still time for him to reveal what the longer term strategy on technology is going to be.
Right. I guess, I'm struggling with this idea that a better demonstration of this technology would be to put the reactor on the moon where it could do something useful.
But it wouldn't be Marshall then. It'd be Glenn.
Okay.
I would like to add to that. Also, just chucking it out into space, you don't have to worry about final disposition of the fuel. You don't have to worry about human rating. You don't have to worry about landing it. It's just chucking it out there is a lot easier than trying to land it on the moon and deal with shielding and scattering off the regolith, because we don't really know a lot of the radiation transport properties of the regolith too. So there's a lot of issues with just putting it on the moon to begin with.
Okay, Lucas, maybe this would be a good time to drill down in a little deeper on the technical details here. So, as I mentioned in my opening remarks, to get me really excited about applications of nuclear reactors to propulsion, you need to hit that magic 1 kilowatt per kilogram of specific power.
Mm-hmm.
Is there potential that nuclear reactors in space could get to that level of power density? What would be the path to get us there?
I just want to say that that's kind of for the vehicle, right? So for the propulsion system itself, you probably want to get a little closer to 10.
That's asking a lot. If you could just get the power supply to it, even at 500 watts per kilogram for the outer solar system, you'd be really happy.
Yeah, and
right,
I think there may be a pathway to 10 kilowatts per kilogram potentially. Jeff, you saw my Twitter post a while back, and you messaged about that. But I can get into that later. I have an animation that we produced that kind of explains that whole concept. But the short answer is yes. And I'd like to talk about how these systems scale, because that's really important. So you mentioned like 10 or 20 watts per kilogram, but that's for like kilopower. That's 1 to 10 kilowatts. At that power level, the mass of the reactor core and the shielding dominates. The radiators, which dump all of the waste heat from the power conversion system, are kind of negligible. But when you get up to like megawatts, then the reactor and the shielding are actually negligible, and it's the radiators that start to dominate, because the reactor and the shielding don't really get much bigger. So as an example of just a simple example of how the shielding scales, going from 1 kilowatt to 1 megawatt, you have to add 3 10th value layers to the shielding thickness. So a 10th value layer is just the thickness of shielding that drops the radiation dose by a factor of 10. So you're going up 3 orders of magnitude in power, but you're only increasing the shield thickness by 30%-ish. So you're increasing mass when you have extra diameter and stuff. You're increasing mass by like 50%, maybe double. But the power has gone up a factor of 1,000. So the shielding doesn't really get much heavier. The specific power of the reactor and the shield together don't really, they become negligible at higher powers. And that's where radiators start to dominate. But you can get probably radiators down to like single digit, like kilograms per square meter. I did experiments when I was at Atomos that was carbon fiber and heat pipes. And there's some details of that I'm going to keep to myself, but we found some really ingenious ways of bonding heat pipes to carbon fiber that conducted heat very well, and it was very scalable. We could make the radiators as big as you want, and it was a very cheap manufacturing process. And there's nothing crazy about that. It's just, metal, sodium heat pipes and carbon fiber. And I think radiator tech is going to improve regardless of power source, because if you're building megawatts of solar farms for data centers or anything, you're generating huge amounts of power. And if the thing that's taking that power is electronics, like GPUs or whatever, you have to get rid of all that heat. So for that reason alone, I think radiator tech is going to continue improving a lot, regardless, independent of
It's hard
nuclear
to
power.
bifurcate though, because like the applications are so different in terms of the temperature range that you can work in, as well as whether you can do localized emission.
Yeah, but you get the general idea, right?
Yeah.
I mean, high temperature radiators are going to be useful in a lot of applications outside of nuclear power, and
Yeah,
there's
so
always
let's,
been,
go ahead.
and you know, right now I think I don't know if I can share my screen. I have a spreadsheet up. I can show the effect, but basically, yeah, I show a nuclear power system in my simplified model here. It crosses a kilowatt per kilogram at around 3 megawatts because it scales very non-linearly, like I was saying. Reactor and the shielding just don't increase in mass that much.
Yeah, let's talk a bit more about radiators here, maybe for the audience's benefit. If you're running a nuclear reactor in space to generate electrical power, what you're doing is you're taking a heat source, this hot core of the nuclear reactor, heat not that useful of a form of energy, and you're trying to convert it into electricity, which is a much more useful form of energy that you can use to run electric propulsion. So if you're doing that, you're going to be operating a thermodynamic cycle. So you're going to be operating something like a Brayton cycle using turbo machinery or a Stirling cycle. And you're always going to be bounded by an efficiency in the limit, the Carnot efficiency. And what that means is for every kilowatt of electrical power you generate, you're probably going to need to reject at least 2 kilowatts of thermal power if your efficiency is around 30%, 30, 40%, probably a reasonable limit. So that's why on Earth, when we build nuclear reactors, they either have those iconic, hyperboloid cooling towers next to them, or you build your nuclear reactor by a lake or a river or an ocean because you need a cold sink to reject heat to if you're running a cycle to make electricity. So in space, as we know, there's nothing to dump heat into other than radiate away to the blackness of space. And that's what radiators are. So they're on, for example, the International Space Station. Not all the panels you see on the ISS are solar panels. Some of them are radiators. They use a loop of ammonia to reject heat from the space station into radiation in space. So if you look at the one that's on the space station, I think it can radiate about 10 watts per kilogram. So again, about what our nuclear reactors are. And again, I want to make this really clear. I'm a professor of thermodynamics, so what do you expect here? I want to make this really clear. You sort of have to reject heat to make electricity. Okay, it's not like, oh, it's inconvenient that our reactor is overheating and we got to dump away some heat. No, it's in the rejection of heat that you generate electricity. And you got to reject, again, like twice as much heat as the electricity you want to generate. So this is non-negotiable if you're trying to generate power, electrical power.
But
so
what is negotiable is what temperature you do it at.
Okay, but it's got to be on, thermodynamically, the radiator is operating on the cold side, right?
Right.
So,
So that
you want to keep the cold side cold and the hot side hot.
Well, that's one way of looking at it, right? What are you optimizing for? Are you optimizing for efficiency, or do you not care? Or are you optimizing for watts per kilogram? Because if you're optimizing for watts per kilogram, what you do is you let the efficiency come down a little. You make the hot side as hot as you can so that you can make the cold side a lot hotter. So that you can, because for what you didn't mention in that little thermodynamics course for the audience is radiator area required goes inversely with the 4th power of the temperature. So you double the temperature, you've reduced the area of the radiator required 16 times. It's a big deal, and we have options. They won't be the first thing we try, and they shouldn't be the first thing we try. But we have options for running reactors with the hot side much hotter than we typically do in ground power. And in space applications, that makes perfect sense because on the ground we have water to dump heat into, and in space we don't. Cooling is precious, so it makes sense to run the whole cycle hotter. And that won't be the first thing we do, but this technology has legs. It has the ability to grow into a farther future. One of my
Okay,
personal thumb rules is about technology is, if you're going to invest in something, you want something that's got a growth path to getting like 10 times better than what you're doing. If it only gets 2 times better, you probably should stick with what you're doing now because you can just do more of it.
Yeah, but we need to get about 100 times better for where our reactor designs that I've seen. Again,
But what I'm saying is, compared to chemical, the ability to get 10 times better than what we can do with chemical is there in nuclear electric. That will not be the first thing we demonstrate, but it has the ability to scale up to that kind of performance.
I would also, I would add to that, Jeff, you kind of stole my thunder. I was going to explain that, but you beat me to it.
I'm sorry, repeat, please.
You stole my thunder. I was going to explain all that, but
you'll do it better.
I'll just add to that it's not just the power system and the propulsion system. My old boss at Atomos, she did a very detailed study on NEP, but she wasn't just optimizing the power system; she was optimizing the entire vehicle. So there's a whole lot of things on the spacecraft that are all very interdependent. So you have the power conditioning stuff that takes the electricity from the Brayton engine and turns it into a voltage and power form that the spacecraft can use and the propulsion can use and all that. That's a lot of big, heavy hardware. You have this big, long truss, a boom that supports the radiators and stuff and so on. The length of that boom is going to add mass. The longer the boom, the lighter your shield. You can make your shield thinner because you have more distance. The half angle of the shield can affect the geometry of the radiators. And there's all kinds of knobs and things that are all interconnected. So if you can optimize the entire vehicle as a system, you can get really good performance. And that's what she found. And she said she initially thought that she had done something stupid and made a mistake because she goes, this doesn't match any of the literature I'm seeing. This has got to be wrong. And she kept digging into it and working on it and found that no, it was actually correct. It's just that nobody has ever done it that way. If you look at Prometheus and these other NEP programs, like they optimized piecemeal. Right, everybody had their specialty and they farmed it out, and that's not a good way to do it.
One of the things I'd like to foot stomp that you mentioned, people don't talk about enough, is the power conversion electronic state of the practice in space is really from the Jurassic era. Yeah. Because the space radiation environment won't let you use the kinds of techniques that we use for advanced switching power supplies on Earth, their performance compared to what we're doing on Earthside stuff is very poor. So there's a lot of opportunity, and I would love to see NASA funding some research on just that one piece of the puzzle of power conversion machinery, because there are approaches to go after that could let us knock a lot of mass off of the system there.
I'm actually really curious to see how there's been a lot of development in the last 10 or 20 years in like big high-powered semiconductors. I mean, you think about the superchargers for EVs, those things can dump out hundreds of kilowatts to charge your battery, and it's smaller than a fridge.
Yeah, no, but that's what I mentioned. The problem is those particular devices that have done amazing stuff on ground power. Ground power is revolutionized in the last 10 or 15 years. But unfortunately, those devices have very high electric fields in them, and if they get hit by a cosmic ray, they punch through and destroy themselves. Okay. So there are good reasons why the space guys haven't adopted that art, and that means there's a good opportunity to start investing into technologies that could give us that kind of performance, but also perform in the space environment.
I got you.
So I'm not going to let this go on the point about radiators, though. So radiators we have today on ISS reject about 10 watts per kilogram. The most advanced radiator designs I've looked at, I'm kind of fond of the liquid droplet radiator, where you transfer heat to a liquid and you spray the liquid out into space, more or less because it was invented by my PhD advisor in the 1980s. That I thought about the best they ever thought they could get. This is on paper early in the design, when your numbers are usually pretty optimistic, would be maybe rejecting 5 kilowatts per kilogram. There's something called the Curie point radiator. I know Jeff is fond of. Similarly, pretty advanced idea. Again, studies there, no doubt forward leaning, about similar numbers. I think maybe rejecting 2 kilowatts per kilogram. And again, that only is the thermal heat you're rejecting, the amount of electricity you can generate is probably half of that. So, again,
Yeah,
we're
I
down
think you're
at
talking about
1.
radiators at room temperature. You talk about
Well,
kilowatts
no.
per square meter.
Well, I'm trying to convert it into mass. Is the numbers
right,
I've seen.
but
Let me just finish my rant here. So again, I keep coming back to this number. Yeah, maybe we get to kilowatt per kilogram, but again, this company, I misremembered the name earlier. I think it's StarPath. You can go with your credit card in today and buy thin film solar panels that are 3 kilowatts per kilogram. They cost $15 a watt. Yes, you need a boom and so on to deploy them. I get it. But, here's a technology that's here. You can get it, buy it. It's space rated. And we're laying out a long, multi-year, hundreds of millions of dollars, billions of dollars to might get us to the kind of power densities that solar photovoltaics can get today with nuclear power. So it looks like Jeff might be frozen again. So Lucas, it's back to you to see if you can give us some hope.
I wanted to just quickly mention we did have a question a while back about when do we know for sure that it's an escape velocity trajectory that's planned for it.
I mean, my understanding is it is being sent to Mars. I saw something in a PowerPoint slide saying it might be a 12-month duration mission, but I think it will probably use chemical propulsion to do the escape, and then it may just do the electric propulsion as a demonstrator along the way. It's similar. Some years ago, the Japanese launched a mission to Venus, and along the way, they deployed a solar sail as a technology demonstrator. It really propulsively didn't do anything to help them get to Venus, that it was just an opportunity to do a technology demonstration. Right. So that's my best understanding of what I've seen. I don't know, Lucas, if you've seen anything more. Jeff, the question we got.
I was listening again.
Okay,
I get booted, but then I hang out in the lobby until somebody lets me back in. I can answer that question if you want. I mean,
please go ahead, Jeff.
Yeah. I mean, I was singing this song back in 2009. You can buy 6 kilowatts per kilogram cells today, but unfortunately, that doesn't make you a 6 kilowatt per kilogram array. Not even close. If you want to use the same logic you do where you sum up the mass of the systems individually, the array, the mechanical support, and the thing that holds the panels out currently weighs close to 2 kilograms per kilowatt. So the cells could go to 0, and you're not beating 500 watts per kilogram.
Yeah.
There are absolutely things you can do about that, and I would love to see them done. But clearly, that's the interesting technology. That's one of the interesting technologies for moving around the inner solar system. That's not such an interesting technology for moving around the outer solar system. And if you're talking about applicability to surface power, the moon has this inconvenient thing where it's dark for 2 weeks. So we have a neat portfolio of technologies. There's no one ring to rule them all.
Yeah, me and Ozan actually had a long Twitter conversation about this a couple of weeks ago. And you said you had come up with ideas for like rolled mylar tubes and things like that. But I think what Jeff is getting at is that even if the cells are 0 mass, like the specific power is always going to decrease with area. It might decrease very slowly, but as power increases. But as the arrays get bigger, you need more structure.
Yes.
And it scales sublinearly. So no matter how lightweight the structure is, it's going in the wrong direction.
Yeah, Lucas, another thing I'd like to talk to you about is my understanding all the past space-rated nuclear reactor designs I'm aware of, going back to SNAP-10 and SP-100 and Topaz, all used highly enriched uranium. I believe the plan here is to use high-assay, low-enriched uranium. And be interested if you could kind of fill us in on what the trade-offs and issues are there.
Yeah, so a lot of this has to do with politics and non-proliferation. I mean, if it was up to me, we'd just use our old plutonium that's sitting around because it's such a great fissile. You build a reactor the size of your fist, and but that's just not feasible politically. The security around it, high enriched uranium is anything above 20% U-235 concentration, and they classify that as high enriched. Really, you need higher enrichment than that to build a bomb, but there's a whole. It would take too long to explain. But basically, they cut off at 20%, and there's good reasons for that. Below 20% is low enriched, and the definitions are kind of arbitrary. But above 5%, which is typically where power plants operate, 5% enriched, that's LEU, and then up to 20% is HALEU, or high assay low enriched uranium. Now, ideally, you want the highest enrichment you can for a space reactor because it makes the reactor very small. You need you have more U-235, more fissile material per cubic centimeter. You can get a smaller critical mass. At lower powers, like kilopower, crusty, enrichment really matters because that's the majority of the system mass. But like I was saying earlier, when you get up to like megawatts, the reactor and radiator mass are kind of negligible. Maybe not quite negligible, but they don't really matter that much at high power. So once you get up to hundreds of kilowatts or megawatts, it doesn't really make much of a difference, the enrichment.
I'd like to
Yeah,
add
it's
a quick thing to
something
that.
like a Crew Jupiter mission. You ideally want several hundred megawatts. So
I was going to mention on the small end, one of the reasons why we so urgently need to qualify even low power space reactors is for outer solar system missions, practically speaking, it's nuclear power or don't go. Jupiter you can have a discussion about, but like if you're going out to the Kuiper Belt, it's a nuclear power system. And our current capacity to launch those missions is severely constrained. We used to make the Pu-238 that we used on the RTGs as a side effect of nuclear weapons material production. We aren't doing that anymore. Then we used to buy it from the Russians because they had it left over from their nuclear weapons program. We aren't doing that anymore. We've pretty much used up the stockpile, and the current production rate is tiny. It's not enough to support the pace of outer planet missions that we're used to. Now, there are alternatives to sound the song I'm always singing. I'd love to see a portfolio of other RTG sources being worked on because there are alternatives. But one of the other alternatives is just don't use RTGs and put small reactors on them. But you have to qualify the small reactors before you can do that.
Yeah. And Jeff, you might be able to, you might have more insight into this than I do, but my understanding is one of the reasons they don't want to use reactors on planetary missions, or they haven't shown interest in it, is because there's no flight heritage, right? They don't want to risk an expensive science. They care more about the science than the technology, so they don't want to risk the science on an unproven thing.
This is I was smiling when you were doing the history of GMO, because like with the planetary scientists all said, we just give us 5 conventional missions. Well, yeah, of course. The science community's approach to anything is, millions for scientists and not a penny for propulsion. Because they say it's because of the risk, but it's ultimately because they're scientists, not propulsion guys, and they want to. If you ask a scientist what we should spend money on, the answer is more scientists. So yeah, there's all kinds of reasons why I don't want a reactor on my spacecraft. What it comes down to is if I said you were going to put a reactor on my spacecraft, there'd have to be money spent on the reactor. And if I say I don't need a reactor on my spacecraft, they don't have to spend that money, so they hope they'll spend it on me.
Well, I'm going to push back on this a little bit. First of all, at least the space scientists deliver. Okay, when I think about what NASA has done in the last 30 years, that's changed our view of the universe. It's Hubble and James Webb Space Telescope and the Mars rovers and the Jupiter and Saturn orbiter. This is mission-driven, science-driven, and not. We have to worry about keeping NASA centers alive and people employed.
That's not quite fair. It's just a question of which NASA center you want to keep employed. I mean,
Okay.
why do you think these scientists get their budget? You know, the answer is yes. We have successfully failed to advance technology on 100% of the technology demonstration missions that we haven't funded. And if talking about manned space flight, yes, it's a big, expensive program, and it takes longer to finish than a presidential administration. So they keep getting their objectives changed. Which is to return back to what I said earlier in the thing. If you want to actually start getting some results flown, speed is life. You got to do missions that can be designed and built and flown in a short time.
Okay, let me put my Jeff Greason reality hat on here. So if you want your mission to fly, you have to get the science community on board. You have to show up in the decadal surveys. And our colleague Les Johnson, spent his entire career at NASA trying to get a solar sail flown, and I've heard him say this comment very frankly: if you want to fly your pet technology, you've got to convince the scientists you can do a mission with your technology that would not otherwise be doable.
And my position, you're absolutely right today. And as long as that's the case, we will continue to advance no technology, because the only way to get a technology funded is for it to be on an approved mission. The only way for it to be an approved mission is for it to require no new technology. QED. So okay. If our posture going forward is the science community controls all technology funding in NASA, we're done.
Well, I think the onus is on us, the propulsion engineers, to do better. When I look at missions that claim they need nuclear electric propulsion, they tend to be these really contrived missions, like let's go to Triton, the moon of Neptune, collect a sample and bring it back to Earth. It's a real stretch to come up with a mission that really needs NEP. And I think we have to do better. I think we have to come up with really innovative things you can do. And to zoom out the conversation here a little bit, the only two things I ever come back to that really require advanced propulsion is to do a sprint mission to Mars with a crew, with astronauts, to get around the cosmic radiation exposure issue, where you can go and come back and not wait for the next synod. You can go and I know, Jeff, you put a lot of thought into this too. How do we do a 6-month round trip mission?
And the other thing I think about, NEP is not the answer to that.
Agreed. Okay. And then the other thing I think about doing is, going and doing a real interstellar precursor mission, or I'm quite fond of the solar gravitational lens concept. You go out 550 AU and turn the sun's gravitational field into a telescope that gives you an amplification factor in the billions. Or I hope that Brown and Badigan at Caltech find their Planet 9. That would be pretty cool. That would probably be out there at 400 and 600 AU. So, if we find a hypothetical planet.
I think you passed over sample returns a little too casually. You say the science community delivers, but let's take a look at the Mars program. Okay, I mean, we've been successfully sending robotic probes to Mars, for what, 15, 20 years now. And the program is extremely successful. Because no mission answers the questions. So at the end of every mission, we have the justification all built in for why we need another mission. And the community is well employed, and everybody gets to make their career out of it. But it's been since Viking that we've flown a life detection experiment. Why don't we fly another one? And the answer is because if we flew another one, we'd be done. Right? We would either find life and we'd be done, or we would not find life and we would be done. Schrodinger's scientific result is very successful from a funding perspective, but I'm not sure that from the taxpayer's point of view, this is actually such a big win. Sample returns answer real questions. You get the material back, you get to put it in the lab, you get to do all kinds of tests with all kinds of instruments that you did not have to fly to the planet. I think if we had a form of advanced propulsion, whatever it was, that will let us do sample returns from, for example, the Jovian or Saturnian satellites, or from Triton, we'd answer a lot of questions. And I don't think it's true that the scientists wouldn't love to have those sample returns, but they're never going to ask for it, because if they ask for it today, they're afraid the budget to do that propulsion development is going to come out of their budget.
Yeah, USNC did a NIAC 5-6 years ago. But they were developing a Cobalt 60 RTG that had very high power density, which is actually related to the concept I was doing. But their whole study was basically a sample return from Oumuamua. Because they're like, well, we don't know what this thing is. It's probably not an alien spaceship, honestly. But whatever it is, it's weird. Wouldn't it be fun to go out, catch up to it? One of these interstellar objects that passes through our solar system randomly. Go up, catch up to it, grab a sample, and come back. I don't think that's a fringe mission. That would be very, very scientifically interesting to have something like that. Have something just sitting in Earth orbit ready to go when one of these objects passes through, and then we can go intercept it. But you'd need crazy propulsion for that. But I would also add that it's not just propulsion. These small reactors, like what they're talking about here, is not a crazy design. I'm pretty sure I know basically the reactor they're talking about. The recurring cost for these reactors would be similar to an MMRTG, I think. So once you had these, now you have 20 kilowatt reactors that cost as much as an MMRTG, and you can get more of them than RTGs. Now you can.
You're not limited to one every 10 years. You can buy, if you want 5 a year, you just make them.
Yeah,
exactly. Yeah, and for the audience, those are RTGs are a few hundred watts. So
they're about 100.
X.
So you're going from 100 watts to 20 kilowatts.
That's a lot higher bit rate. Power is bits.
Yeah. So more data back, and I'm sure instrument designers can come up with ways to use that power too.
We did get a question earlier that was about do we know what enrichment level the Chinese lunar base surface reactors are going to use?
I'm sorry. Do we know what level?
Enrichment level. Highly enriched or high assay, low enriched.
Oh.
The Chinese, I'm sure they're using HEU. They don't have the political issues that we do. We have a lot of other issues. That seminar I went to last week was all about nuclear launch. All of the barriers of nuclear sessions. Most of the people in the room were lawyers, right? We had sessions that were all about indemnification and Price-Anderson Act and all this stuff. And I think that's one of the big reasons that they're actually doing it with the DOE, because DOE can actually indemnify the launch under the Price-Anderson Act, the same way that they do the RTGs. If you do it with a private company, there's no existing legal structure for indemnifying the launch of a nuclear system. So
it might be worth mentioning for the lay audience here that one of the nice things about a reactor as opposed to an RTG is when you launch it, it's radioactively cold.
Yeah.
The one that you're going to fly to space, you don't turn on until it's in space. So the material in the reactor is basically a lump until after you turn it on.
I had.
I just think some people are scared of it, but
I was going to come up with a visual aid. I have a big Fiestaware soup bowl with the uranium glaze on it. I was going to use that as a visual aid, but it had it packed up. It just moved.
I've got a banana in the other room, but yeah, and of course you could say some people are scared of it. Some people are scared of eclipses. If your standard is some people are scared of it, you need a better standard.
Yeah.
Yeah, Lucas, can you tell us, can small companies work with high assay, low enriched uranium? What?
Yeah.
Again, the other thing I sort of gave me. Triggered my spidey senses about this is, Isaacman has championed this idea of leveraging partnerships with private industry and capitalizing on the new space revolution and small, nimble companies. And then I think about, building a nuclear space reactor is like the least likely thing that would ever capitalize on this new environment.
It's not as hard as you would think. So there's companies, you look at Antares is one. They actually got a batch of HALEU from the DOE, and they're building a reactor at INL right now. They're planning to go critical this summer. There's a couple other companies doing the same thing. Small, basically critical assembly demos. So it's a reactor that doesn't generate power; it just reaches criticality. But that's the big benchmark. If you can do that, you can generate power too.
That's really what high ALAU is for.
Yeah.
It's spicy enough to be useful, but not spicy enough that it's hard to get a hold of or hard to handle.
Right, and there's actually a big push to develop the supply chain for HALEU right now, because so many microreactor companies like Antares and Ayalo and Radiant and X Energy all need HALEU for their reactors.
Okay, so these are like these fourth generation reactors we hear about, small modular reactors. They would all use HALEU.
Yeah, and that's why there's a huge build out of enrichment capacity in the U.S. because previously we've been buying a lot of that from Russia. But most of our all of our power plants just ran regular LEU, which we have capacity to here. We have research reactors that use higher enrichment, but they buy that from BWXT and they get it from Russia. Yeah.
5 minute warning, guys.
Oh,
there. No, I'm sorry. I was on the time. We're good.
19 minutes.
Oh crap. Okay.
Yeah, well, I mean, this might be a good time to start wrapping things up. I think this has been a really good discussion. I learned a lot. Is there anything that you wanted to register with us that might have missed in the discussion? I mean, Ozan, is there anything that you feel we wanted to cover here that we didn't yet?
Let's see. So we have a number of comments about what do you need for propulsion and surface power, and I just want to broadly address those. People who are commenting on you need a mix of high thrust and low thrust for taking advantage of NEP for going to Mars, which I think the four of us agree, at least in the foreseeable future, that NEP is not the right solution for that.
For the high thrust part, it's very difficult to deliver high thrust with NEP. Yeah.
Or but even low thrust, but faster than chemical. As far as do you need the mix? Probably, and there are some people who are saying, chemical is not the right way. Really, chemical and NTP, nuclear thermal, is a little bit of a wash. And whichever is going to be the lower cost solution. Like they have similar,
which is going to be chemical because we have it.
Yeah.
They have similar. I love the technology of nuclear thermal. I'm sorry, I didn't mean to step over you. I love the technology of nuclear thermal, and had we finished its development in the 1960s, we would surely be using it today.
Yeah.
But the fundamental problem with it is, compared to chemical, it's one of those kind of factor of two improvements. Yeah. And it's an expensive development program to get through. You look at that and you say, gee, how many missions are we going to have to do to get that improvement before that pays back the investment? Or should we just launch twice as much chemical propellant?
Yeah, and they're expensive to build too, because they need a lot of fuel that's very specialized, and they self-destruct.
My opinion is every technology is good for something, but it's not the NTP is not like the great white hope that cures all problems. It's kind of a niche technology, and I don't think it's a mistake to say let's focus on NEP because they're the same technology tree feeds your surface power and your space power.
Right.
You're going to need both of those things. And while NEP might not be the right answer for going to Mars, there's lots of missions that we want to do in the future for which it is.
Yeah, right. Exactly. And I would decouple the reactor and the propulsion. The reactor is just the power supply. You can use that power supply for any number of things. And it's not like Basic and the Hall effect thruster guys are going to stipulate you can't buy their thrusters if it's not nuclear powered.
I really want to register a point I've heard Jeff make in the past. So this is really just me channeling Jeff Greason in front of Jeff Greason here. Why nuclear thermal propulsion? So we're talking about NTR now, nuclear thermal rockets, was so appealing in the 1960s in the Apollo era. Was in those years, no one could have imagined launching more than 4 Saturn V's a year. Okay, I think that was the maximum cadence that was ever hit, was 4 Saturn V launches in a year.
And lots of people imagined it, but
yeah, if you say, hey, if we could replace an upper stage, with a nuclear thermal rocket that has twice the ISP, we can deliver this much more payload to the surface of the moon. It's called your gear ratio. You know, how much kilograms can you put on the surface of the moon? And so that was quite appealing.
I mean, you
now,
got like 1.6 times the payload out of a Saturn V to the moon
Right.
that you were going to with a nuclear thermal stage, and it was almost ready to go. I mean, it's truly like criminal negligence of the U.S. technology base that we abandoned the program when we did, because it was ready to go. You know, the rockets were done, they were qualified. They were trying to get one ready for Apollo 20 if there had been an Apollo 20. You know, so. But the problem is that the legal and regulatory environment is unrecognizable now from what it was then. You know, it would cost us God knows what, but a very large multiple today to do the program of what it cost to do then. And it was so long ago that we can't really pick it up from where we left off. We almost have to start over again. Now, there are people working on it. There's companies working on it. I wish them all good things. But my own gut feeling with NTR is it's a niche technology whose time has passed. It didn't get ready in time.
Where would most of that cost be, Jeff? In the
facilities,
in the ground testing facilities?
Yeah,
Right.
I mean basically there's not a bunch of private companies lining up to build the facilities to fire large thrust nuclear thermal rockets indoors.
Yeah.
And you know I used to joke when I was on the Augustine Commission that if you ask NASA for what it's going to cost to build that facility, the answer is however much you have times 2.
Yeah. During NERVA, they were able to fire the rockets outdoors and just blow the exhaust into the atmosphere. The problem is, like I said, the cores kind of self-destruct. You're running hydrogen through this. When hydrogen gets really, really hot, it's like the worst possible solvent. It'll eat everything. And so you have to have these specialized fuel coatings and whatnot that hopefully erode slowly. But they erode.
Little bits of the reactor are breaking off into the exhaust, and
Exactly.
you're spreading it all over the landscape. And you know, you just couldn't do that today.
Yeah, you'd have to have an exhaust scrubber, which is an enormous facility.
And these are big rockets. I mean, because nuclear thermal rockets are high thrust, it's not a little trickle of gas. If you take a look at the videos of these things running, they were like 20,000 pounds of thrust.
Yeah,
you know,
like one of the test stands.
That's a lot of volume flow rate of material that would all have to be handled and scrubbed, and you'd have to assure everybody that there'd be no leakage of nuclear material. I mean, in the original NERVA program, on purpose, they made one break just so that they could practice cleaning it up. Can you imagine doing that today?
There's some great photos of that. I think there might even be video. You can see all the glowing chunks of core sparkles in the air.
So it's I mean, at the time we should have just finished it, and then we'd have it today, and we would have been using it all these years. But you know, technology is path dependent. We are not starting from where we could have been. We're starting from where we are, and starting from where we are, I'm not sure it's a winner.
Yeah. I can think of some like applications eventually. I think it's just going to be a little bit of an optimization, probably not for Mars, or at least not all the way to Mars. I think orbital tugs, where you can you get a lot of cycles out of a high cost, high initial capex system. That has some possibilities. The other thing that I want to mention is regarding surface power. People say, well, you need nuclear for surface power. And I will gladly admit there are a lot of applications for nuclear surface power on the moon and on Mars, and certainly in the outer planets where it's better. It's just better. It's not strictly necessary. There are ways to get megawatt, gigawatt, terawatt, petawatt scale power with other means. I mean, mainly solar. But
yeah,
we had when my previous company was going through the process of getting acquired, I was trying to pitch my work to the acquirers, and they were trying to do asteroid mining or something. And I was trying to explain to them that, yeah, you can do that with solar. It's not going to be great. Me and my colleague, we made a detailed pitch deck explaining breaking down exactly how they compare, and it's orders of magnitude different. Like, yeah, you can do it with solar, but nuclear is much better.
I would push back
remember
on
the-
the orders of magnitude. I think they're
It was a lot. It was a huge difference because it wasn't just the mining operations itself; it was also transporting lots of material and all this other stuff. And I was using the activated radioisotope systems I mentioned earlier. But yeah, it was like the analogy I gave them was like, yeah, you can build canals, but what if your competitor starts building a railroad? They're going to bury you. Like it's better. It's going to outperform. It's better. It's more economical. It's more expensive to build initially because you got to do all the R&D on the locomotives. But long term, they're going to beat you. You know.
And there are, I mean, it's not scale invariant. You know, the if you think about like the moon, if you said I'm going to scale to gigawatts of power, you'd say, well, then you want to do it all solar, and you want to do, you know, then there are overnight storage systems that use mostly in situ material. You know, you can imagine scaling to that, but to get to that scale, you first have to have an industrial operation on the moon that makes things. You know, it's very hard to It's not impossible. Nothing's impossible, but it's very hard. It's very suboptimal to try to bootstrap your way all the way up to an industrial civilization with 100% solar all the way. You know, you look at the first part of that scaling curve and God, if I'd had 50 or 100 megawatts of nuclear power, that first part of the scaling would have gone a lot better.
Yeah. Of course, now we are, operating in a world where we could easily imagine several kilotons landed at, less at lower cost than what we would spend on R&D for an alternative approach. And with that, you don't necessarily have to do a gigawatt scale overnight storage. What you can do is, set up multiple solar panels in geographically varied locations, and then string up transmission lines within that 1 kiloton budget.
Yeah, you're going to find the stringing of transmission lines along 100 kilometers of virgin lunar territory is not such a trivial activity.
Yeah,
I mean, it's awesome, but
like I said, I'm not saying it's impossible, but this is why technology should be managed as a portfolio. Right.
Yeah.
You shouldn't approach it and say, I have the one killer thing that's going to solve all of my problems. You know, there are several different technologies we'd love to see pursued in parallel. Nuclear is the most expensive one. For political factors I explained earlier, there's going to be one expensive one, and it's going to be done at Marshall. So we might as well get some good out of it. And you can say, well, that's not the way that we should run our space program. And maybe it's not. You could say that's not the way we should run our government. And maybe it's not, but it is.
I would also say that there's another aspect to this. And I think seeing a lot of these small companies developing microreactors and not spending huge amounts of money, they're not spending billions and billions of dollars. I look at Antares, they're not a very big company. Radiant's not a very big company. Allo is not a very big company, but they're building reactors. Fuel is not, and like I told you, Andrew, in that Twitter thread, like a lot of the problems and a lot of the cost is in institutional friction. Government program management is not great. Small, scrappy companies can do a lot with not much. SpaceX is like the perfect example of that, right? Just apply those same principles to nuclear power.
Yeah.
Honest to God. And then the nuclear industry is very, very, it's very much like the space industry was 20 years ago, right? You had small companies that were trying to do stuff and nobody took them seriously. And the big companies spent lots and lots of money to do not much. That's kind of where it's at now. It's getting better. And so I would say that extends into space nuclear. And once you have a pathway for reactors in space, I know a lot of these companies, Antares is very actively interested in space nuclear. So it's not just a government program. NASA is not the only player. And once you prove that, yes, reactors work in space, you can do it, that opens it up for private investment. and there's going to be interested. There's going to be interested parties that want to get involved in that, and people will find ways to use it. And it won't
Okay,
be
well,
super expensive.
I guess the last, I think we need to wrap up. I think the last thought I'd like to leave people with is, give me a moment here. Is I think a lot of times in the technosphere, I hear people talk about nuclear energy and space propulsion. Reminds me of people saying, quantum mechanics is this deeply mysterious thing we don't fully understand, but it's deep. And human consciousness is this deep, mysterious thing we don't fully understand. There's got to be some connection there. And you go down that path, you end up, in Deepak Chopra land. And I see something similar in the technosphere. Is right now nuclear engineering, nuclear power seems, edgy and cool, and it's all the new buzzwords now. It's pro-abundance, it's pro-effective accelerationism, or whatever these things mean. I don't know. I'm pro-nuclear because it works. But people think, okay, nuclear, cool and edgy, and what could be cooler and more, interesting than advanced propulsion for deep space? So that's got to be the answer. And present company excluded, but I find when I talk to people about this, that sometimes is all the further depth of their thinking. And I just want to register that it's got to make sense. It has to enable missions that we cannot otherwise do, that I think in the near term has got to do amazing science that can't otherwise be done. I cannot figure out any way nuclear power for propulsion, nuclear electric for propulsion for crewed missions makes sense in any capacity I can think. So, well, this has been, really great discussion. I learned a lot. Appreciate your time. I still haven't heard anything that's got me, super excited about this. And I guess maybe Jeff, I want to push you to answer the question that you didn't want to answer at the beginning. Is this your vision of what NASA should be doing in terms of technology demonstrations?
NASA should be doing technology demonstration. This is a technology demonstration. So I'm glad to see if they can actually do it, if they can actually fly fast and show that they can fly something. I think it will be a good step forward. Is this the highest leverage thing they could do? No. Is this the only thing they should be doing? Absolutely not. But for reasons discussed, I think there's programmatic, non-technical considerations that make this an obvious place to start. And I hope, and I have nothing to go on here other than hope, that this is the first of many and not the first and last.
Yeah, I would add to that. I don't think this SR1 mission lives or dies on whether it enables NEP. It lives or dies on whether we can field a space reactor program again. We haven't flown a reactor since 1965. The people that did it are all dead or retired. We need to figure out how to do that again. Once we do that, it kind of breaks the psychological barrier as well. And that was the reason I did the Pathfinder program at Atomos too. It was just a critical assembly on a small set. But it just, you got to get past that first of kind. And
everything must be done for the first time once.
Yeah, exactly.
Okay, Ozan, back to you. Thanks again for hosting us.
No, thanks for having this conversation and suggesting this, Andrew. Jeff and Lucas, thank you for showing up and bringing your insights.
Yeah, this is fun.
Yeah.
Thanks for having us.
Bye.
Bye-bye all.
Bye.